Okay, let's unpack this. I have to be honest with you. When you first sent me this PDF, I thought you were pranking me.
Oh, come on.
No, seriously. I thought, surely this is a test to see if I'll actually read the attachment.
Why? It's a breezy weekend read.
Breezy. The title alone is enough to induce a migraine. I'm holding it right here. Normalization-induced curvature, a universal mechanism for interference, geometric phase, and dimensional emergence.
It sounds like a lot, I know.
That sounds like something you'd find in a locked filing cabinet at CERN, or maybe in a secret alien communication log, and does not look like deep dive material.
It definitely sounds intimidating, I will give you that. It's dense, it's heavy on the Lie algebra, and it uses words like symplectic without apologizing. But, and this is a big, but hidden inside that thick forest of mathematics is a master key.
A master key. You promised me this key supposedly unlocks how the universe builds reality. That is a very tall order for a PDF.
It is, but the paper delivers. It challenges the most fundamental assumption we all make about existence. That space is a stage.
A stage.
Yeah. Usually we assume geometry is just there. The floor, the walls, the vacuum of space. It's the background, it's the passive container, and then the particles or people or data points are the actors moving around on it.
Right. The stage exists before the play starts. The floor is there before I walk on it.
Exactly. This paper says, no. It argues that geometry is not assumed, it is generated.
Generated.
It's a byproduct. Space, dimensions, curvature, they are all created by the simple fact that actions interact with each other.
So, to put it simply, the actors don't walk on a stage. The stage appears because the actors are walking.
That is a perfect way to visualize it. And the mechanism that builds the stage, it's something called non-commutativity.
Okay, non-commutativity. We're going to need to break that down immediately. It sounds like a legal term for a bad commute to work.
It's much simpler than it sounds. It's the hidden law of order. Here's the test you can do in your head. Take two operations, let's call them A and B.
Okay, A and B. Got it.
Now perform them. Do A, then B. Then hit reset and try doing B, then A. If the result is exactly the same, if the order doesn't matter, we say they commute.
Okay. Like putting on my left sock, then my right sock. Doesn't matter which I do first. The end result is socks on feet.
Exactly. In that case, geometrically, you've just traced a line. You went there and back, effectively. No drama. The path closes perfectly on itself. But what if the order does matter? What if doing A then B puts you in a totally different state than doing B then A?
Like putting on socks and shoes.
Right. Socks, then shoes. You're ready for work. Shoes, then socks.
For ridiculous.
You look ridiculous and your socks stretch out.
Yeah.
The result is fundamentally different. That is non-commutativity.
Ugh.
And here's the magic insight from the paper.
If the order matters, you don't trace a line, you trace a loop.
A loop. Walk me through that.
Well, think about it spatially. If path AB takes you to point X and path BA takes you to point Y, there is a gap between those two outcomes. You aren't back where you started.
To connect them, to make the system consistent, you have to close the circuit. You've created a shape.
And shapes have area.
Correct. And area implies curvature. And if you have curvature, the universe is forced to pop up a new dimension to accommodate that shape.
Whoa, slow down. You're saying that just by doing two things that don't get along, two things where the order matters, we are physically forcing a dimension to exist.
That is the radical thesis here. The paper calls it the master equation. It claims that quantum mechanics, how light waves interfere, and even how we analyze statistical data in spreadsheets, they are all just different symptoms of this one geometric story. They're all responding to the fact that order matters.
Okay, I'm hooked. But I want to get under the hood. We can't just wave our hands at master equations. The paper talks about something called the commutator being the source of this curvature. Is that, like, the receipt for the difference?
Ideally put, in mathematics, specifically in Lie algebra, the commutator, usually written as x and y inside square brackets, is literally the calculation of the conflict. It measures result, xy, minus result, yx.
So if the commutator is 0, order doesn't matter. We are in sock-sock territory.
Right.
If it's not 0, we have conflict.
We have conflict, and therefore we have geometry. But to understand the title, normalization-induced curvature, we have to talk about the cone.
The cone. I saw this in the notes. States inhabit a cone? Are we talking about ice cream, traffic cones, or something else?
Something a bit more abstract.
Yeah.
Think of a cone in 3D space, expanding outward from a central point. The paper uses this to describe systems where the scale doesn't change the identity.
Oh, okay.
Think about a song on your stereo. If you turn the volume knob from 2 to 10, it's louder, but it's the same song.
The state of the song, the melody, the lyrics hasn't changed, just the magnitude.
Exactly. Or think of stock market data. If every stock price doubled overnight, the relative performance, the pattern of the market, would be identical. This means these systems live in a normalized world. We care about the pattern, which is like the angle on the cone, not the volume, which is how far out you are.
Okay, so we're living in this cone world where size is irrelevant. How does that connect to the curvature?
This is where the math gets beautiful. The master equation states, curvature of C equals the commutator minus the projection.
Okay, lay it on me in plain English. What are we subtracting here?
It means that curvature, the bending of reality that we can actually measure, is simply the part of the commutator, the conflict, that survives when you strip away the volume knob.
Let me try to paraphrase this to make sure I've got it. So I have two actions. They conflict. That conflict creates this commutator value. But because we live in this normalized world where scale doesn't matter, we sort of filter out the scaling part of the conflict.
Yes.
And whatever is left over, that residue, that is curvature.
You nailed it. Think of it as a shadow. The conflict between actions is a complex, multidimensional thing, but when you shine a light on it and project it onto our observable world, the shadow it casts is what we call curvature, or geometric phase.
That is a fascinating way to look at reality. The shape of the world is just the residue of things happening out of order.
It reframes everything. Curvature isn't just a static bump in the road. It's the active result of processes clashing. And it gets even more specific. We talked about loops earlier. If I asked you to walk a loop on a grid, up, right, down, left, what shape is that?
Up, right, down, left, that's a square. Simple.
In a flat world where things commute, yes. But the paper reveals a surprising detail. When things don't commute, the minimal loop that captures this curvature isn't a square.
It's not.
It's a hexagon.
A hexagon. Why a hexagon? Is nature just really into bees?
It's about logical efficiency. The paper describes a specific path sequence. It's written as A dot B dot A dot B inverse dot A inverse dot B inverse. It's like a complex dance step.
Okay.
If you try to close that loop using a square when there is conflict non-commutativity, the ends don't meet. You end up with a gap.
Because A then B didn't take me to the same spot as B then A. The square is broken.
Exactly. To close the loop and capture the curvature, the math forces you to add extra steps. The simplest non-trivial shape that closes that gap is the hexagon.
So the hexagon is the shape of logic when orders conflict.
Yes. It relates to something called planar root system geometry. The paper proves that if you have three unit vectors that are constrained to sum to zero, which is what happens in these closed loops, the mathematics forces them into exactly 120-degree angles.
And 120 degrees is the internal angle of a hexagon.
Precisely. It creates what mathematicians call an A-2 root system. The point is, nature isn't just being artistic with snowflakes or honeycombs. In this context, the hexagon exists because it is a mathematical necessity derived from the commutator. It's the only way to resolve the conflict of order.
That is wild. It's like the universe has a default setting for handling disagreement, and that setting is make a hexagon.
It's the most efficient way to enclose the conflict.
Okay, so we have the math, we have the hexagons, but I'm the listener driving to work right now asking, so what? Does this abstract algebra actually show up in the real world, or is it just a theoretical playground for physicists?
Oh, it shows up everywhere. Let's look at physics first. You remember the double slit experiment?
Classic physics. You shoot particles, electrons, or photons through two slits, and on the back wall, you don't just get two piles of bullets, you get an interference pattern, stripes of light and dark.
Right. Now, if you open a standard textbook, it explains that as waves overlapping. Crest meets trough, they cancel out. Crest meets crest, they amplify.
Sure. Wave mechanics 101, ripples in a pond.
But this paper flips that on its head. It says those interference fringes, those bright and dark stripes, are literally just projected commutators.
Wait, the stripes on the wall are algebra.
They are the visual manifestation of the order of operations. The paper defines constructive interference, the bright spots, as happening when the cone curvature is non-zero. Destructive interference, the dark spots, happens when the curvature is zero.
That's a totally different mental model. You're saying the pattern of light and dark is actually a map of where the operations commute and where they don't.
Precisely. The cosine fringe pattern, that wavy line of intensity, is the master equation in action. You are seeing the curvature of the operator order projected onto the wall. The wall is displaying the math of non-commutativity.
That completely changes how I picture that experiment. It's not just water waves slushing, it's the geometry of the setup asserting itself.
And it's not just quantum physics. This was the part of the paper that really surprised me. It applies to statistics and data science just as much.
Okay, now you're stretching. How does a spreadsheet have curvature? I've stared at Excel for hours and it looks pretty flat to me.
It sounds strange, but it obeys the exact same law. The paper discusses the covariance matrix.
Okay, for the non-data scientists listening, covariance just tells you how two variables change together, like ice cream sales and temperature have high covariance, they move together.
Correct, but the paper presents a concept called covariance symplectic area equivalence.
That is a mouthful. What does that mean for the person analyzing the data?
Think of it this way. The paper proves that the determinant of that covariance matrix, basically a single number representing the relationship, is equal to the square of a symplectic area.
Area again. So data takes up space.
If the variables are correlated, yes. If the determinant is greater than 0, your data has inflated. It has created a 2D geometry. It encloses an area.
And if it's 0?
Then the dimension collapses. It flattens into a line. The paper describes this as the classical analog to the Heisenberg uncertainty principle.
So if I'm looking at a massive data set and I calculate this determinant, I'm essentially checking if my data has popped into a 2D shape or if it's still flat.
Yes. And if it has inflated, that area is once again generated by the non-commutativity of the underlying signals. It's the same story as the hexagon and the light waves. Whether it's photons hitting a wall or stock prices fluctuating, if there is area, there is a commutator driving it.
This leads us to the four-way equivalence. The paper presents this as a sort of grand unified theory for this concept. It seems like the author wants us to realize these aren't four different things.
They're the exact same thing, wearing different costumes. The central theorem proves that four concepts, which we usually treat as totally separate subjects in university, are identical.
Let's run through them. I want to make sure these land.
Number one, the commutator. That's the algebra, the difference in order.
The socks versus shoes conflict.
Number two, curvature, the geometry, the bending of the space.
The shadow cast by the conflict.
Number three, area, the volume enclosed by the loop we talked about.
The hexagon.
And number four, and this is the big one, emergent dimension, the growth of the system's rank.
That phrase really stuck with me, emergent dimension. It sounds like a sci-fi movie title.
It's the most profound implication. The source proves that if the commutator is non-zero, the rank of the system must grow.
Define rank for us here.
Rank is essentially the number of independent directions you can move in. A line is rank 1. A plane is rank 2. The paper shows that you cannot solve the conflict of non-commutativity in the lower dimension.
The conflict is too big for the line.
Exactly. If A and B fight, they can't stay on the line. The math literally requires a new direction, a new degree of freedom to open up to accommodate that loop.
That sounds almost biological, like the system is evolving because it's stressed.
That's a brilliant way to put it. The stress of the incompatible operations pushes the system out of the line and into the plane. It forces it from 1D to 2D. Non-commutativity isn't just a quirk, it is the engine of dimensional growth.
So if we didn't have conflict, if everything happened in any order perfectly, we'd be stuck in a flat, one-dimensional universe.
You wouldn't have a universe at all, really. We'd have a static line. The richness of our 3D and 4D reality exists because variables interfere with each other. The complexity of the world is a result of things not getting along algebraically.
That is surprisingly poetic for a paper full of matrices. I want to circle back to something mentioned near the end of the paper. It was a theorem about the evidence gap. It felt like a philosophical mic drop.
Oh, yes. Theorem 5.1.
It says the gap between what you expect and what you see is equal to the lie bracket.
Correct. Imagine you are navigating. You move forward 10 steps, then back 10 steps. You expect to be at 0, back at the start.
Right. Net change 0. That's the logical expectation.
But if the space is curved, or if the operations don't commute, you aren't at 0. You're slightly off. You missed the mark. That distance, that evidence gap, is exactly the commutator.
So the error isn't random. The error is the geometry.
Yes. And this leads to the universal normalization principle mentioned at the conclusion. We often look at noise in a system, whether it's static in a radio signal, weird fluctuations in a market, or just things not adding up in our lives, and we dismiss it. We say, oh, that's just error. That's just noise.
Clean up the data, right? Ignore the outliers.
But based on this paper, if that noise has a structure, but it has a non-zero determinant, It's not just noise. It might actually be the universe trying to grow a new dimension that you just haven't recognized yet.
That is a provocative thought. We're sitting here trying to filter out the noise, but the noise is actually a new room opening up in the house of reality.
It forces you to ask, is your noise actually curvature? Are you ignoring a dimension because you think it's just an error in your spreadsheet?
It really makes you look at chaos differently. It's not disorder, it's higher order geometry that we're too flat to see.
We're trying to fit a hexagon into a square hole and calling the leftover bits noise.
Exactly. So, to summarize our journey today, we started with a title that scared the living daylights out of me. We learned that geometry isn't a pre-existing stage, but a byproduct of action.
We found out that when actions don't commute, when order matters, they create loops,
Hexagonal loops, specifically,
Okay.
which create area, which implies curvature.
which we see as interference, fringes in physics, or covariance in data.
And ultimately, that curvature forces the universe to expand its dimensions,
Hmm?
all driven by the simple fact that A then B is not the same as B then A.
It's a beautiful, unified picture.
It makes you want to go out and do things in the wrong order just to see if you can create a new dimension in your living room.
I wouldn't recommend it with household appliances. Putting the metal in the microwave before turning it on is a bad kind of non-commutativity.
Fair point. We'll stick to the theoretical dimensions for now. Well, on that note, we're going to wrap up this deep dive. It's been a trip through the geometry of order.
A hexagonal trip at that.
Indeed. We hope this master key helps you unlock a new perspective on the chaos around you. Maybe it's not chaos. Maybe it's just geometry waiting to be noticed. Thanks for listening.
Until next time.
See you in the next dimension.